My name is Bagyzhan Bagymkyzy, and today I will present our work entitled Exploring Resonance in Cancer Cells by Wave Equations. This work done together with my professor Dong Wei. He's my supervisor. And the main idea of this talk is very simple. We want to understand how soft cells, biological soft cells can respond to vibrations. So in particular, we are interested in cancer cells. As an example, we used MCF7 breast cancer cell. And it is, so we are interested in this topic because here this cancer cells can mechanical, so not only biological can change the cancer cells, also they can be changed, their mechanical properties also can be changed during disease or metastasis. And so let me continue with the abstract part. So here we studied the nonlinear damped nonlinear oscillator, and this is our main model. Here, if you look at this U, U means the indentation or displacement of a cancer cell. Here, the C means the damping coefficient, and the FC means the external force, nonlinear contact force, and nonlinear contact force. So here we use the variational iteration method and the approximation in order to find the approximate analytical solution. And then, as an example, we use this breast cancer cell. And so results show that the resonance depends strongly on effective cell stiffness, and while near resonant excitation can produce bit-like amplitude modulation. And so why this topic is important and why we decided to study this. And so how I mentioned before, these cancer cells not only biologically different from normal cells, they're also different mechanical. So for example, the stiffness of a cancer cell can change during metastasis or disease. And this is important because stiffness controls how cell deforms under some mechanical sound or vibrations. And if we know the main response frequencies of a cell, we can better understand how the cell reacts to some external forces. And as an example, so this histotripsy, so University of Michigan first studied this. So histotripsy use short ultrasound bursts to create very tiny bubbles that mechanically can damage, can break the tumor issue. And in October 2023, even Food and Drug Administration allowed marketing of this histotripsy system for liver tumors because there were very good cases. And so our main goal, so not model the full histotripsy process, but at least so it's our goal is basic, like we want to find the main response frequencies of a soft cell and understand how large the motion can become. So this is our main mathematical model. Here, if you see, we have two system of equations, nonlinear. So we consider two AFM tip geometries. AFM means atomic force microscopy. And we have two tips. As I mentioned before, in our equation, we have the nonlinear part. And in nonlinear part here, we use the Hertzen model. Hertzen model has these two types, conical type and the spherical type. And the difference between these two equations is that in the nonlinear part, power here is the quadratic, here is the 3/2. And here the k, is our constant. The in E means the Young's modulus, and the nu is the Poisson ratio. And here alpha is the half angle of the conical tip. So okay. So how we solve these two equations? We solve it using VIM Pada approximation method. VIM means variational iteration method. First, we constructed variational iteration method. So first, we constructed this correction functional using this VIM method, and later we generated after we generated VIM iterations starting with initial guess. In our case, this is A1. And then after several iterations, we obtained this polynomial approximation solution, our U of t. But so here, obtaining just polynomial approximation is usually good only we have very small time, short time. And so in order to improve this, we applied the Laplace transform. And after we applied the Pada approximation, we used the Pada approximation. And finally, we applied the inverse Laplace transform in order to get our final solution. And so here, our final result is not only a polynomial, it becomes, now it becomes a sum of cosine terms. Getting sum of cosine terms is very useful because this cosine term directly show the main oscillation frequencies of the system. So here, let me share with our main results. This the first result here. This is for conical tip case. When the AFM indentation has a conical tip. Here, this is our solution with cosine terms. This means the amplitude, and the omega means here the frequency. So, as I mentioned before, the important point is that the solution represented as a combination of oscillation modes. And the second result that we get, this is for the second equation, with a spherical tip. Here also, amplitude amp means amplitude, omega means the frequency. So let me move. So then we simplified our model to undampened case. So setting just C, this damping coefficient to 0, and so we just simplified our equation 1 and 2 to these two equations. So here, because here we don't have any damping, the system is conservative, and this means that the energy is preserved. So why we studied this case, these two cases? So the first reason is that undamped case is easier to compare with already known analytical results. And it also helps us to check whether our VIM Pada approximation method gives a correct frequency and the phase. So using the same method, we obtain this. For this undamped case, we use the same method steps, VIM iteration, then Laplace transform, Pada approximation, and the inverse Laplace transform. If you look here we have this two solutions, like with 3 cosine terms and with 4 cosine terms. The 4 frequency approximation just gives better accuracy, and later I will show how it looks like. Professor, we studied this equation in his work. He studied this case, and this is our model. And in his Professor's Wei's work, he got the exact analytical solution, and we just compared our approximate solution with his solution, and matching by matching, here we have that in our case n is equal to, and the exact solution. So exact generalized sign solution looks like this, and our VIM PAD approximation solution looks like this, and here I showed this graphically. Here in these graphs we compared this two cases, the exact generalized solution, sign solution, and this our approximated solution. And the first graph shows us this is the conical tip case. The first graph shows us with the 3 cosine terms. The second graph shows with the 4 cosine terms. That is why these 4 cosine terms, this 4 frequency approximation improves this agreement, and so we can say that comparison supports the validity of our approximation method. These graphs, yeah, so here this is for the spherical tip, the same way we just compare with the exact generalized sign solution. And here are the graphs. The first graph shows the approximated 3 cosine terms, and here, if you look, we have in this case the 4 cosine terms approximated, which is compared with the generalized sign function. Yeah, by graph we see that it's validated. Now let us move to the bit, so bit-like modulation. Here, this is our numerical part. We use all these 4 intrinsic modes, and we used as an example MCF7 breast cancer cell. And here we have these 4 frequencies, and the important point is that here the response is not produced only by 1 frequency. It is so it is produced by 4 frequency, and here we got this, and when we have this several frequency presented, their interaction can produce amplitude and can produce this amplitude modulation, and that amplitude modulation we call bit-like behavior. And here we see the full 4 envelope looks like this, and let me move to the next slide. And here you see this 6 pairwise interaction, and if you look at this table, we see that the closest pairs is the F1 and F2, and their difference is equal to 31 Hz. And here we have the bit period, which is equal to this 32 milliseconds. So it means this is so in comparison with others, it means this is the slowest visible modulation. The other peers also will contribute, but because their frequency is much larger, they will create very faster oscillator components. And here, the numerical graph so shows here this four frequency response that I mentioned before. And if you look here, this all four frequencies shown in this graph. And the main idea is that, as I mentioned before, because these two frequencies, F1 and F2, are like close to each other, they can show this envelope and slow modulation, and yeah. So here the yellow line is also the an envelope guide. And the other one is very fast frequencies. This is our full frequencies. So in conclusion, let me summarize. In conclusion, so what first we modeled this AFM indentation of a soft biological cell using nonlinear oscillator, and second we just consider this Hertzen model. The first one is the conical with conical tip, and the second one is the spherical tip, and the third we applied the VIM and the PADA approximation in order to get the approximated solution, analytical solution. And fourth, we validated our method by comparing it with generalized sign functions. And so as you have seen that the results are good and it's validated. And finally, we used as an example MCF7 cancer cell, breast cancer cell as an example, and we studied the full frequency response. And here we showed that the bit-like modulus, bit-like modulation is produced. So yeah. So further, we are going to study the, this is for 0D case, and further we will study the 1D case, 2D case, and the 3D case, and the etc. This part I already discussed, and so this is a reference list. Okay, thank you for your attention. If you have